Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we will continue expanding on our understanding of the applications of Gauss Law. Go watch the previous videos if you haven't yet, so that you understand every explanation. Today we will introduce cylindrical symmetry. We will first start with the simplest case, an infinite wire. After that, we'll give it some volume and consider an infinite cylinder. And lastly, we will understand what happens if the charge density of the cylinder is not constant. So, let's start! Great, let's start with the case of the wire. Imagine we have this infinite wire with a positive charge density lambda. That's not quite a lambda, I'll redraw it. That looks a lot more like it. So, if we want to consider the electric field at some point, for example over here, we'll have different charge elements that are going to work in pairs, dq1, dq2, and they're going to give us a total electric field. This is E1 and this is E2 in this direction. So a very similar thing to what happened on infinite seats is going to happen in these infinite wires or cylinders, that these different segments of charge are going to cancel each other so that the electric field is going to point radially outwards. In this case, as this is really one-dimensional, not two-dimensional, as in the case of the plane, this electric field is not going to be uniform all throughout the space, but it's only going to depend on the radius, this distance along the radial distance from the wire, at a dependence of 1/r, as we'll see. In these cases, for cylindrical symmetry, we're going to use a cylindrical Gaussian surface. We'll draw it over here, and we're going to have it such that this area is not going to be contributing because it's parallel to the electric field, and the same will happen for this area over here. The only part that is going to contribute is the cylindrical surface, the cylindrical cover we could call it. Now, if we express our electric field and the flux in this situation, we are going to have that it's going to be equal to E in this direction, because it's going to be constant over here and in every direction, times this area, and that area is going to be equal to the circumference of this cylinder, that is 2 pi r, times this length, which we are going to define by L. So it's going to be 2 pi r L. Now, the charge enclosed is going to be equal to this linear charge density times the charge segment, the length of the charge segment we're considering. So it's lambda L over epsilon naught. We see that we can have some cancellations over here, this and that, and we find an electric field that is going to be lambda over 2 pi r epsilon naught, and it's going to be pointing in the r hat direction, that is radially outward from the wire. As we see, it does indeed depend on the radius, but it has only a 1/r dependence, not the 1/r square dependence that a point charge has. Great, now let's give it some volume to our wire and consider an infinite cylinder. In this case, we're going to have now two differentiated regions, and they are going to depend on R, as this situation is radially symmetric. So R, speaking of R in cylindrical coordinates, not R in spherical coordinates. We're going to have the radius of this cylinder to be capital R, and we're going to have our coordinate R hat. We're going to have two different regions for R less than capital R, which is going to be the inside of the cylinder, and R bigger than capital R, which is going to be the outside of the cylinder. Let's start considering the outside of the cylinder. In that case, we're going to define a Gaussian surface that's going to be once again a cylinder. So you can easily imagine the electric field is going to be very similar to the one we had with our wire. It's going to be pointing radially outward over here, and on the inside we're going to have the same thing, radially outward, but at a smaller magnitude. If we carry out our flux analysis, we see this doesn't contribute, this side, and this side over here doesn't contribute either. So we just have that our electric flux it's equal to the electric field at those points times the area, and by defining this radius as R and this length as L, we find this is 2 pi R times L. That is the exact same analysis than what we did for the wire. Now finding the charge enclosed is going to be a little bit more difficult. We're going to have rho times pi R squared, this area, times length, and it's going to be divided by epsilon naught. We can see there's some cancellations over here with the pi and the L, but really not too many, and we end up with an electric field E equal to rho R squared over 2R epsilon naught, and it's going to be pointing radially outwards and on region 1. Alright, let's this be region 1 and inside region 2. Now let's consider what happens on the inside, and to do that we need another different Gaussian surface, which we're going to do over here. We're going to have, as I said before, a radially pointing electric field. Once again, we're going to take R as the radius and L as the length. If we carry out a similar analysis, which for the flux part is going to be the exact same, we find this is going to be equal to E times 2 pi R, the circumference times the length. But now it's a little bit trickier to find this length, this charge, to find this charge enclosed. We're going to have rho times pi R squared, little r squared, because we're not considering the charge that is outside of that region, only the one inside of it, times the length over epsilon naught. In this case, we're going to have a little bit more of cancellations. The pi and the r is going to go, and we're going to be left with, oh, and the L also cancels, and we end up with E in the second region equals rho R over 2 epsilon naught. Now let's check if this electric field is really continuous to find out if we did a good job. E of r, and this is in the r hat direction, is going to be, for r bigger than r, capital R bigger than r, we need to specify, we're going to have this expression, rho r squared over 2r epsilon naught r hat. And for r, little r, less than capital R, we are going to have this expression over here, rho r over 2 epsilon naught r hat. What we see is that if we substitute, let's make this side the one that's equal, if we substitute r equals to capital R in here, we get a cancellation of one of the factors of r squared, and we end up with this same result with r substituted capital R. So our function of the electric field is actually continuous and it works out. Alright, now let's try to explore what happens when the charge density of our cylinder is not uniform. We're just going to explore the inside region because the outside region is pretty straightforward. It's almost the same thing as we did earlier. We will define our same Gaussian surface over here, cylindrical, obviously. It's going to have length L and radius R. Now, if we carry out our flux analysis, it's going to be, as I said, the exact same as we did before. This is pretty analogous to the case we found on the earlier video about non-uniform slabs. We are going to have E times 2 pi RL. But now, when talking about the charge enclosed, that is when things get more complicated. We're going to have 1 over epsilon naught, and now we need to define the charge enclosed as an integral. The integral over the volume of the charge density dB. That depends, sorry, not on x this time, but it depends on r. Now, this is multivariable calculus. We find that this is BR times R dr d theta and dx, because this is the dx region. So for d theta and dx, it's going to be pretty straightforward. That's going to be 2 pi, and that is going to give us an L factor. So we're going to have 2 pi L over epsilon naught, because we're integrating from here to here and all over the angle theta. It's going to go the integral for r from 0 to r of BR squared dr. And this is pretty straightforward. It's just 2 pi BL over epsilon naught times r cubed over 3. Let's denote that. That is the dummy variable. Now we need to equate both sides of the equation, and we find that the electric field is going to be equal to the 2 pi RL cancels, and you get B r squared over 3 epsilon naught. And we need to stick the r hat vector to it. And this is the electric field inside a non-uniform cylinder. That is all for today. I hope you understood everything and that now you have a more clearer idea about how to use Gauss law in cylindrical symmetry situations. Next video we will exploring spherical symmetry, and we will end up with the applications of Gauss law. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!